Actually, yeah, I will speak about the all-scale assimilation of the SEVIRI water vapor channels in our regional NWT system, which is the ensemble Kalman filter. I will start with an overview on our regional system. So this is the icon model that we run in a 2-kilometer horizontal resolution and 65 vertical levels. And the data assimilation system is a LATKF with 40 members and hourly cycling. And up to now, as observations that we assimilate in the routine, we have radio sounds, of course, and synop data and the Arab and Mode S data. And in addition, the 3D radar reflectivity and radio winds that we assimilate in the LATKF directly, but also we apply a latent heat nudging. And since 2 months, we have an additional data source in there, which is the visible channel of SEVIRI, which has been prepared by Bach for operations. These are the measurements at 0.6 micron. So this is available during daytime because this all-scale reflectance is a fraction of incoming solar radiation scattered back to the satellite. Yeah, and it's sensitive to vertically integrated cloud water and cloud ice and the particle size of the constituents. This gives mainly neutral impact for upper air forecast verification, but is beneficial for the surface verification of clouds and radiation. Yeah, but now I want to talk about the 2 water vapor channels of SEVIRI, here marked in red and light green. So this gives us quite additional information to the reflectance of the visible channels. So the right top figure is the reflectance, and the bottom 2 figures are for the same scene, the water vapor channels, and we see that this is gives us quite a different view. Whenever we want to assimilate anything in the LATKF, we have to think about localization, of course, and vertically, while the satellite radiance is an integral measurement over the whole vertical column. So basically we have 2 options. Either we just do not localize vertically and let the ensemble background covariance matrix take care of the spread of the increments. And actually this is currently done for the visible channel in the routine. However, there's the other options to assimilate, to assign a height where the satellite radiances are most sensitive and then localize around this height. This can be either done based on the Jacobians, because in the infrared regions we have these sensitivity functions as output of the RTTOF K module, which is a special module of the forward operator. However, this is expensive for operations. So there's the other options. Another option that we chose here is based on the transmission. The transmission is the standard output of the forward operator, and we assign this height around which we localize to the height where the transmission as seen by the satellite has dropped to 1/2. I show 2 examples for that. One is here a column where there's no cloud cover. It's a cloud-free scene, and there the transmission function for the 6.2 micron channel, well, it's 1 at the top of the atmosphere, of course, and drops in the region where it is sensitive. So we assign here this vertical level, and for the 7.3 micron channel, this region is broader, and so we set this level a bit lower where the transmission is 1/2. Whenever we have a cloud, the situation is different. Here, this transmission decreases in a much more narrow region, and then the height is the same for both channels, as we cannot see through the cloud in this infrared region. Okay, the other aspect we have to think about is, of course, the specification of the observation error. And as you know, the observation error is the sum of instrument noise, representativity error, and forward model error. And the last two parts are larger for cloudy scenes than for clear sky. And for this, to model this dependency, here I use a estimator well known in literature. This is the symmetric cloud impact by Okamoto et al. And here this cloud impact is estimated by the difference between the all sky brightness temperature and the clear sky brightness temperature, which is both provided by the forward model and averaged of the first guess and the observation. Then if you plot this, probably some of you know these graphs. So if you plot this on the x-axis and then on the y-axis you plot the standard deviation of the first guess departures, you get this blue line behavior typically, which means if both model and observation are cloud-free, you get very low standard deviations, and then they increase when one of both is cloudy, and it decreases to some extent if both are cloudy. And to model this observation error, I tried first this red polynomial fit and keeping the errors high from higher cloud impacts. Actually, this didn't give so satisfactory results, so I tried different inflation techniques, like here in purple and yellow, and actually very good results were obtained by this yellow line. So this is what I use in the following. Probably this then takes into account the observation error correlations, this inflation. And here's an example for the 7.3 micron channel. Then the observation error in case of clouds is between 5 and up to 10 or even maybe 12 Kelvin, and it is only 2 Kelvin for clear sky scenes. Okay, now I want to show some results. I compare here two experiments. The reference is just our routine setting with all operationally used data, including radar data and latent heat nudging and the visible channel of SEVIRI. Then the experiment that I compare contains the two water vapor channels in addition. While in all sky assimilation mode, I apply a thinning to which refers to a scale of about 12 times 12 kilometers over our model domain. Excuse me. I have a vertical localization which is quite coarse for the water vapor channels around the level which I told you. And for the visible channel, we found it beneficial if we assimilate the water vapor channels also to localize the visible channel vertically around 800 per hectopascal. So let the water vapor channels take care of the higher troposphere and the visible channel of the lower troposphere. And the horizontal localization is 25 kilometers. My experiment period here is 4 weeks in summer last year. And I show you first the brightness temperature distribution for this period for the two channels. And what we see is, well, they look similar for observation and first guess. However, what we always see is that we have too many low brightness temperatures for the model for the first guess. So we know that in ICANN-D2 we always have too many high clouds. Yeah, but if we in our experiment where we assimilate this satellite data, we get a better match of the distributions. The effect is still there, but is considerably improved. Now another evaluation of the assimilation cycle. So this is the RMSE of the first guess cycle for black, the all sky brightness temperatures, and in blue, this is clear sky, so where the cloud impact is less than 1 Kelvin. And what we see is, that for all sky, the errors vary, of course, depending on cloud cover. And for clear sky, they are very low. And for the bias, they are even lower. They are for clear sky almost 0. And actually, in these experiments, I don't apply any bias correction for this data. And yeah, it's always, the bias is always negative for the all sky, because we have this effect that we have too many high clouds in ICANN-D2. Yeah, so that was from the assimilation cycle. Now I come to results of the forecast runs. So this is the brightness temperature verification, so against the radiances themselves for 24 hours. And we see that here the SEVIRI water vapor experiment reduces the RMSE up to about 15 hours for both channels. And for the bias, we see this cold bias in the reference experiment in red, and this is decreased in the SEVIRI water vapor experiment. So this looks really nice. I now show the comparison against radiosondes of these two experiments. So green means with the water vapor channels we have an improvement, and we see we were hoping that for the moisture, the QV, we see an improvement in the upper troposphere and middle troposphere, but in addition we also see some slight improvement for the temperature profile. For the wind speed and direction in the upper two panels, the effect is more mixed. For the surface verification, we see a positive impact on total cloud cover. However, we see a worse effect on the high clouds, and also partly as a effect on the diffuse radiation. And this is a bit contradictory, because the moisture in the upper troposphere is so much improved. And also a colleague of mine did a verification against high clouds from a satellite product. So there's a nowcasting SAF cloud product where you can get the high cloud cover from. And this, you can see here that the equitable threat score, which should be high, is better for the SEVIRI water vapor experiment.
Annika, you have 3 more minutes.
Yeah, that's fine. Yeah, and the frequency bias, which should be as closest as possible to 1, is also better with the water vapor channels in there. So for the precipitation verification, we don't see any effect, at least for this period. This is a fractional scale score for the 2 experiments for runs initialized at 0 UTC and 12 UTC. And here we don't see any really an effect. Yeah, to summarize, by assimilating this data in all sky approach, we see that we really have a nice benefit on the upper air humidity and simulated radiances in 24-hour forecasts. And we have a slightly smaller positive impact on total cloud cover and the temperature profiles. Despite these positive impacts, we see a negative impact on the high clouds observed from ground stations, which is a bit contradictory. We're still trying to find the reasons. Well, high clouds observed from the ground are, of course, tricky anyway, because if you have low or mid-level clouds, they cannot be seen. So this is anyway a restriction. So, but also maybe there's a problem in the parameterization of the high clouds in our model. We have to figure this out. But well, this we are still looking at, but we plan an operationalization of these data in the next months. And yeah, just to mention this, yeah, as you probably know, the Meteosat third generation, the first satellite, has been launched December last year and is now in the commissioning phase. So soon, in the near future, we will skip then from SEVIRI to the heritage instrument FCI. Yeah, I thank you for your attention.
Thank you, Dr. Annika. So we have some questions for you. So, Dr. Mazir have some comments on this, that for vertical localization in LETKF, there is a third option of using grid space localization using modulated ensembles introduced by Craig Bishop. At ECCC, we implemented the approach but not transferred to operation yet. So he want to ask another question, that can you give us what is the percentage increase in number of assimilated observations when you switch to all sky as compared to the clear sky assimilation?
Okay, that's a good question. I didn't look at the numbers. Well, of course, it depends. Well, for a regional model, it depends very strongly on the period that you look at. So yeah, actually, I cannot answer that one. Yeah, depends on the weather situation.
Okay, so next question is from Dr. Rakesh. In your system, how much percent error is inflated? Have you done any sensitivity study before choosing error values?
Before choosing some error, well, yeah, I tested different error models, of course, and now the inflation is it's an additive inflation by 1.45 Kelvin. Yeah, and this seems to give very good results. We plan in the future to take into account in the LETKF also the interchannel correlations. So maybe we can reduce this inflation then in the future. Yeah, we will see.
Thank you. So now next question is from Dr. Naker. Do you apply the same vertical localization for all variables, or did you try localizing, for example, temperature and moisture differently?
No, this is in observation space, so it's the same, it has the same effect on all variables in the end.
Okay,
Yes.
so means same inflation is used, localization is used for all the variables.
Mm-hmm.
Okay, so now next question is again from Moisier. Did you do verification against independent observations like GPSRO? Since many of the observations are over ocean, verification again radios only are mostly over land.
Yeah, but our model domain for the regional model is the largest extent it's over land. So actually we have a very good coverage of radio zones there. Yeah, so this is.
Okay, so next question is, do you assimilate the SEVIRI all sky radiance project or the data on original resolution?
Yeah, this is not the all sky product, but this is on original resolution, which I then thin to this 4x2 SEVIRI pixels. Yeah.
Okay. So, one more question regarding the same thing about the implementation of all sky assimilation in DWD. Whether in DWD you are assimilating microwave only or all microwave as well as IR?
Well, this is for the regional model system. There we use all the satellite data in all sky mode. For the global system, which I haven't talked about here, we still use the clear sky, but working on the all sky assimilation. Yeah.
Okay, thank you. Okay, so one last question. So, are you consider hydrometer also as a control variable in all sky?
Yeah, well, in the as control variables, we have the cloud water and cloud ice here in these experiments. Yes.
But individual hydrometers are not the part of the control variable?
The others, they are not.
like individual hydrometers like rain, ice.
Yeah, no, they are not. No.
Okay, okay. And how you take care of the correlated observation in case of the early sky cases?
Yeah, actually, we do not do that now, so that's why we probably need the inflation in the error model, and also we apply the thinning. So this is yeah, future work.
Okay, I think we don't have any further question. So thank you very much, Dr. Annika. So